All right, let's talk about formal charge. Something we're going to need if we're going to differentiate between Lewis structures. What do I mean? Well, let's take a look. I have a deceptively simple molecule here. This molecule does exist, so I'm not just playing something abstract with you here. The question is, what is the bonding like for this molecule? And you're saying, golly, that's a good question. Well, if we just start with our total of our valence electrons, we've got 5 from nitrogen. We've got oxygen bringing 6. We've got chlorine bringing 7. That gives us a total of 18 valence electrons. The question now becomes, how do we connect these guys? All right, well, let's say oxygen's in the middle there, so I'm going to pretend that oxygen's my central atom there. And drawing that Lewis structure cost me 4 valence electrons. That leaves me with 14. Then we want to make our outlying atoms happy, so each nitrogen and chlorine are each going to need 6 more valence electrons to make 8. That costs me 12, so that leaves me with 2. I place those on the central atom, and I'm out of electrons. Ooh, now I have a debate, because I need to form a double bond to complete oxygen's octet. The question becomes, who's going to get picked on? Nitrogen? Or chlorine? Which one of those Lewis structures is correct? Let's make this even more complicated. I just chose oxygen for the central atom because it was in the middle. Who says oxygen's the central atom? After all, it's the most electronegative, not the least. So why isn't nitrogen the central atom? Couldn't we do this again with nitrogen? 18 electrons, but nitrogen's our central atom? Bonded to oxygen or chlorine? That would cost us 4. And once again, we'd have a choice to make. So, which one of these 4 different structures is the correct one? And before I forget, why isn't chlorine the central atom, right? So we could actually have 6 different Lewis structures here. Let me skip to a new screen here real quickly. All right, so for this simple molecule we started off with, we've discovered that there's actually 6 possible Lewis structures. So which of these 6 is correct? What tools do we have available to us to help sort this out? Well, one of the big tools we have is that of formal charge. Formal charge is an accounting method. It's a way of seeing who gains and who loses electrons when a molecule is formed. Formal charge also for our purposes helps us select between competing Lewis structures. So what is formal charge? We know it's an accounting method, and we know it's a saying of who gains and who loses electrons. Now, in theory, when a molecule forms, everybody shares their electrons and everybody benefits, and it's all one big happy family. They wind up holding orbitals, skipping along a path, and singing Kumbaya. Yeah, in your dream. Everybody who's ever shared anything knows they're sharing, and then they're sharing, right? And when you share, somebody always shares more and somebody always takes more. Cynical? Yes, I am. Because after all, if you've ever tried to divide a bag of M&Ms with somebody, unless you've actually sat there and counted out and given one person 10 M&Ms, the next person 10 M&Ms, and gone back and forth like you're dealing cards, you know that somebody always winds up eating more M&Ms than somebody else. Matter of fact, why don't you write down M&Ms? Same way for a covalent compound. Sure, they may all pool their electrons, but when they pool their electrons, somebody winds up gaining electrons or gaining possession of the electrons more than somebody else does. And formal charge is a way of seeing who's gaining disproportionately compared to the other atoms in a molecule when the molecule is formed. Formal charge is assigned to each atom in a molecule. The formal charge for an atom is the number of valence electrons minus the number of bonds the atom participates in minus the number of lone electrons. If we were to look at a really simple molecule here, and we were to look at ammonia, we could calculate the formal charge for each atom. If we were to look at nitrogen, nitrogen is in group 5A on the periodic chart. So nitrogen has 5 valence electrons. In the ammonia molecule, nitrogen is participating in 1, 2, 3 bonds. So I'm going to subtract my number of bonds, 3, then the number of lone electrons. It does not say lone electron pairs. It says number of lonely electrons, right? Lonely electrons are twice as annoying as those couples, so those lonely electrons have 2 electrons. So minus 3 minus 2, so 5 minus 3 minus 2 is 0. So we would say that the formal charge for nitrogen is 0 when it comes to ammonia. If we were to look at the hydrogens, well, hydrogen has 1 valence electron because it's in group 1A. It's participating in 1 bond, so minus 1. And it has 0 unpaired electrons, so it has a formal charge of 1 minus 1 minus 0, or 0. That's kind of boring. Everything's 0 here. Which brings up another point. For a valid Lewis structure, the sum of the formal charges for the atoms in a molecule should be 0. So when we look at our ammonia here, we add 0 plus 0 plus 0 is 0. So we know that's the valid Lewis structure for ammonia because the sum of the formal charges are 0. Well, that's a boring molecule. Everything's 0. Let's look at something where things aren't 0 for just a second here. Let's cheat a little bit and look at sulfate. Sulfite, sorry, sulfite. Shh, don't tell anybody when I said that 8. Shh, I only said 8. You did not hear the 8. Sulfite. Okay, we look at our sulfite. We draw our Lewis structure, 6 from sulfur. Well, I'm going to give you the Lewis structure here right off the bat. You know what? Let's cut to the chase here. There's our Lewis structure for sulfate. Sulfite, I did it again! All right, so there's our Lewis structure for sulfite. Let's figure out the formal charge for each of our atoms here. If we look at this oxygen here, this oxygen has 6 valence electrons because it's in group 6A. So that's my number of valence electrons. Then that oxygen is participating in one bond, right? That one bond right there. How many lone electrons does it have now? It has 2, 4, 6 lone electrons. So 6 minus 1 minus 6 is -1. So that oxygen there has a formal charge of -1. How about our sulfur? Well, before we even move on to our sulfur, all of our oxygens have similar bonding, right? They all have similar bonding, and therefore they're all going to have the same formal charge of -1. That oxygen's -1, that oxygen's -1. Now we look at our sulfur. Sulfur has 6 valence electrons. This sulfur is participating in 1, 2, 3 bonds, and it has 2 lonely electrons right there. So 6 minus 3 minus 2 winds up being a +1. So the formal charge for my sulfur would be a +1. Okay, so +1 for my formal charge on my sulfur here. So what's the total formal charge? So what's the sum of the charges for my molecule? Well, I have 3 oxygens at -1 each, and then I have 1 sulfur at a +1 each, so the sum of my formal charges is -2. So is my Lewis structure valid? Have I made a mistake? No, my Lewis structure is still valid. The sum of the formal charges of the atoms in a molecule should be 0, unless you have a polyatomic ion. Then the sum of the formal charges should be equal to the ions on the charge. So when I added up all my formal charges, I wound up with a -2. And what's the charge on sulfite? 2 negative. So the sum of my formal charges should also be 2 negative. So that means I have a valid Lewis structure. Dr. Kelly, we enjoyed ammonia, we appreciated sulfite, but what happened to the no chloride thing, the NOCl thing that you spent so much time on at the beginning of this lecture? Patience, we're getting to this. After all, I'm a doctor, so you know you have to have patience to deal with me. Ba-dum-bum! Try the salad bar, I'll be here all week. Alright, so let's go back to our previous example, but before we do that, let's real quickly read through those rest of the rules. And I'm hoping that you're going to copy these rules down. If you have to pause the video to copy down those 3 guidelines there, I would recommend you do so. I also hope you're copying down that definition of a formal charge. The formal charges of the atoms in a molecule should be minimized. In other words, we want the formal charges of the atoms in a molecule as close to 0 as possible. -1, +1, -2, +2. We want them as small in terms of magnitude as possible. Small in terms of magnitude. We want them as close to 0 as possible. We've already talked about number 2. Let's take a look at number 3. The more negative the formal charge should be on the more electronegative atom. If we went back to that sulfite example, sulfur had the +1 charges and our oxygens had a -1 charge. Who's more electronegative? Oxygen, right? Oxygen's more electronegative than sulfur. Remember electronegativity? increases that direction, and we said oxygen's the second most electronegative element on the entire periodic chart. So who has the negative formal charge? Oxygen. So that's another sign we have a valid Lewis structure, because the more negative formal charge is on the more electronegative atom. So that's another example there. All right, but let's get back to the problem that started this whole discussion to begin with. Gee whiz, talk about your circumlocution. All right, we have 6 different possible Lewis structures for this same compound. Formal charges can help us figure out which one actually exists, or at least what 2 are involved in some degree of resonance. To do that, we're going to have to assign formal charges to every atom in every structure. A little bit of grunt work, but it's all pretty easy, right? We can all do subtraction. So let's get to it. Let's start with these 2 first. I'm going to figure out the formal charge for this nitrogen here. Nitrogen's in group 5A, so it has 5 valence electrons. That's my number of valence electrons. Minus the number of bonds. Nitrogen here is participating in a double bond, so that's 2 bonds. Minus the number of lone electrons. 2 lone electrons there, 2 electrons there, so it's got 4 lone electrons. Remember, a dash can represent a pair of electrons. I introduced that in the last lecture on Lewis structures, but I'm going to be using it heavily here. But anyway, 5 minus 2 minus 4 is negative 1. So the formal charge for our nitrogen there is a negative 1. So the formal charge of nitrogen there is negative 1. Let's do our oxygen now. Oxygen's in group 6A, so it has 6 valence electrons. It's participating in 1, 2, 3 bonds, so minus 3 bonds. Then it has 2 lone electrons, so the formal charge is a positive 1 for our oxygen. Our chlorine has 7 valence electrons because it's in group 7A. Number of valence electrons comes straight from that periodic table. It's participating in just the 1 bond there. And it has 2, 4, 6 lone electrons. So the total negative charge for that is... So the total charge for that is 0. 7 minus 1 minus 6 is 0. So the formal charge for oxygen is plus 1, and for so we have a negative 1 charge on our nitrogen, plus 1 on our oxygen, and a 0 on our chlorine. Already we're running into a little bit of an issue here, right? Because who's the most electronegative atom in this molecule? Oxygen's the most electronegative. It's, if you checked your electronegativity value, it's 3.5. Chlorine and nitrogen both clock in at 3.0. So oxygen's the most electronegative. So if anybody's going to have the negative 1 charge, who should it be? This guy. So already our Lewis structure is running into a little bit of a problem. But let's keep forward and figure out the formal charges for the atoms in this structure. Let's go with oxygen again here. Oxygen has 6 valence electrons. It's participating in 1, 2, 3 bonds. It has 2 lone electrons. A dash is a pair of electrons. So it's got a positive 1 formal charge again here. Our chlorine this time is going to be different. It has 7 valence electrons. It's participating in 1, 2 bonds, and it has 2, 4. It has 4 unpaired electrons. That gives it a charge of positive 1. Don't make the mistake. Remember, this is chlorine, right? So that's not a pair of electrons. That's the L on chlorine. FYI there. So it has 4 lone electrons because that's an L, not a pair of electrons. So that's +1 for chlorine. Then we come to our nitrogen here. Nitrogen has 5 valence electrons, -1 bond, -2 for 6 lonely electrons, for a total charge of -2 for the formal charge there. So we've got -2, +1, and +1, which all equal to 0, but look at the magnitude. All right, now that we've assigned formal charges to 2 of our structures, let's do a celebrity death match. I know I'm dating myself, 90s MTV series. Between these 2 structures. Which of these 2 structures is the best? Well, both have the sum of formal charges equal to 0. -2 + 1 + 1 is equal to 0. -1 + 1 + 0 is equal to 0. So the formal charges all equal 0 for both compounds, so they pass that test. Let's think about our first rule, though. Our first rule says that the formal charges should be as close to 0 as possible. Well, I've got a +1, -1, and 0 there. Down here, I have a +1, and -2. So the magnitude of the formal charges is higher here than it is here. So the magnitude of formal charge for this structure is greater than that structure. And we want to minimize the formal charges, since if we added the absolute values of these formal charges up here, we'd get 4. We added the absolute value of the formal charges up here, we'd get 2. 4 is greater than 2. So this actually decreases the magnitude of the formal charges. So this is a much better Lewis structure than that. So we can cross this one out already. We know before we even do any of our other structures, that this one's out. This is the better Lewis structure. This is the better Lewis structure because the magnitude of the formal charges is less for this structure than for this structure. So 1 down, 4 more to go. Let's look at our 2 chlorine structures next and do their formal charges. We've got an oxygen here. Oxygen has 6 valence electrons because it's in group 6A. It's participating in 1 bond, and it has 2, 4, 6 lone pairs. 6 lonely electrons, 6 lone electrons. That gives us a formal charge of -1 for our oxygen. Our chlorine here has 7 valence electrons because it's from group 7A. It's participating in 1, 2, 3 bonds, and has 2 lone electrons. So that gives it a formal charge of +2. Our nitrogen has 5 valence electrons, is participating in 2 bonds. It has 2, 4 unpaired electrons, so it has a formal charge of formal charge of -1. I can't subtract today. -1. All right. So we had +2, -1, -1. We look at this, our neighboring structure over here, and our chlorine is going to be the same, again for the same reason. 7 valence electrons, 3 bonds, 1, 2, 3. 2 unpaired electrons. So it's going to be positive 2 for our chlorine again. Oxygen in this structure, however, is going to be 6 valence electrons because oxygen's in group 6A. It's participating in 2 bonds, and it has 4 lone electrons. So its formal charge is going to be 0. Then we've got nitrogen, 5 valence electrons. Now I forgot to draw on a pair of electrons when I drew that Lewis structure there. Shame on me. 5 valence electrons, minus 1 bond, minus 2, 4, 6 lone electrons for a charge of -2 for the formal charge for nitrogen. So for that Lewis structure, our formal charges are going to be 0 for the oxygen, positive 2 for the chlorine, and 2 negative for the nitrogen. Now for both these structures, the sum of the formal charges is 0. And if we did the magnitudes, we'd get the sum of the magnitudes for both structures to equal 4. So how do we decide between these two structures? Which is the best between these two structures? The magnitudes both sum to 4. And so that's not the way to decide it. Look at that last criteria there under formal charges. The most negative formal charge will be on the most electronegative atom. If we look at our structures, we have one structure where nitrogen has a -2 and oxygen has a 0. In this Lewis structure, oxygen's a 0, nitrogen's a -2. Who's more electronegative? Oxygen or nitrogen? Oxygen, right? Oxygen's the second most electronegative element after fluorine. So this Lewis structure is probably a bad Lewis structure because the more electronegative charge isn't on the oxygen. Instead, it's on the nitrogen. So because that negative formal charge isn't on the most electronegative atom, we can rule out that Lewis structure. This Lewis structure is a much better one. Why? Because you have the negative charge on the more electronegative atom. So we've knocked out 2 Lewis structures already. How about we do a little bit more celebrity death match here, and we compare this one with this one. This one, the magnitude of our formal charges, the absolute value of the formal charges, sum to 2. This one down here, the absolute value of the formal charges sums to 4. Remember, your first rule under formal charges is your vowed Lewis structures will minimize the sum of the formal charges. Will minimize the formal charges, get them as small as possible in terms of magnitude. This gets them to a magnitude of 2, this to 4. So this is the better Lewis structure because it minimizes the formal charges. So we can cross this one out. Crisscross applesauce. All right. So now we're down to 3 contestants in our survival pool. And you know one of them's going to be brave and try picking the Detroit Lions. All right, so we need to determine the formal charges for the atoms in this structure. Our oxygen here, 6 valence electrons, 2 bonds, 4 lone electrons, formal charge of 0. This Lewis structure right here, nitrogen has 5 valence electrons, it's participating in 3 bonds, and it has 2 lone electrons. So it has a formal charge of 0. This looks good. We've got chlorine with 7 valence electrons. It has 1 bond. It has 6 lone electrons, so it has formal charge of 0. Wow! So we've got our formal charges there to all sum to 0. How about this structure down here? Nitrogen has 5 valence electrons. It's participating in 3 bonds, 1, 2, 3, 2 lone electrons, so its formal charge is 0. Our oxygen has 6 valence electrons. It's participating in 1 bond. It has 6 lone electrons, 2, 4, 6. So its formal charge is -1. My chlorine over here has 7 valence electrons because it's in group 7A. It's participating in 2 bonds, and it has 2, 4 lone electrons. Don't be fooled. Remember, that's an L. L for chlorine, not a lone pair of electrons. So that chlorine only has 4 lone electrons, and that gives us a positive charge of +1. So you've got +1, -1, and 0. Well, if I'm looking at just this Lewis structure and just this one, who's the better Lewis structure? That first rule says we want to minimize the formal charges. You can't minimize them any more than all zeros. Since all the formal charges in this structure are 0, it is by far a better Lewis structure than this one. Too bad, you lose. New soup for you. All right, so there are 2 contestants left on the island. All other structures have been eliminated. So I've just got to compare this one with this one. Hands down, not a problem. We got a +1, we've got a +1, -1, and 0 going up against a 0, 0, 0. We want those formal charges as small as possible, so the 000 wins. You had a nice run first structure, but you met your match. So that's our best structure. So that's how formal charges can help us. We started off with 6 competing Lewis structures. All of them found homes for our valence electrons. However, we were able to determine the best Lewis structure and how the molecule would actually exist by using our formal charges. So the actual molecule will be most characteristic of this structure. Chemistry's easy, life is hard, yes? What is also hard is life when you don't have a Snickers bar. Why don't you write down Snickers? Everybody write down Snickers. S-N-I-C-K-E-R-S. Snickers. Like chemistry, it's really satisfying. I like making sure my horses are thoroughly dead from the good beating before I send them off to the glue factory, and people are really thinking I hate horses out there. How many times do I use that expression? Talk about beating a dead horse. I think I beat a dead horse when I use the expression beat a dead horse. Whoa, talk about redundant. All right, let's take a look at another way formal charge can help us. And look at another molecule. All right, let's draw the Lewis structure, or Lewis structures, for this molecule. I've got 4 valence electrons from my carbon. I have 6 valence electrons from my oxygen. I've got 2 bromines. Bromines in group 7A, so they each have 7 valence electrons. And I've got 2 of them for 14, so I have 24 valence electrons to build my Lewis structure with. Carbon's present, so by default I can decide it's going to be my central atom with everybody attached to it. That costs me 6 of my that costs me 6 of my electron pool. That leaves me with 18. Make my outlying atoms happy. 2, 4, 6, 2, 4, 6, 2, 4, 6. That uses up my last 18 electrons. I'm out of electrons in my building fund, and who still doesn't have 8? Carbon doesn't have 8. So we've got a dilemma, because now we have 2 possible suspects for double bonding. Is our structure going to be Or now, a lot of you are already saying, well, gee whiz, Dr. Kelly, I know it's going to be this structure because bromine's in group 7A and only likes to form one bond, and oxygen's in group 6A and we know it likes to form two bonds, so this has to be the right answer. Okay, you're right, you got me. But play with me anyway here, right? Don't leave the party early. I promise it's going to get good. All right. If we use formal charges here, we can differentiate between these two structures. So let's assign formal charges to the atoms in both structures. Over here, at this oxygen, oxygen's in group 6A, so it has 6 electrons, it's participating in one bond, and it has 2, 4, 6 lone electrons, so it has a formal charge of -1. My carbon has 4 valence electrons, it's participating in 4 bonds, it has no lone electrons, so it has a formal charge of 0. This bromine here has 7 valence electrons, it's participating in 2 bonds, and it has 4 lone pairs of electrons, 2, 4, so its formal charge is +1. This bromine's bonding is different, so we're going to have to do its own formal charge as well. 7 valence electrons, 1 bond, 6 lonely electrons, so it has a formal charge of 0. So that gives us, if I can clean it up a little bit, -1, +1, 0, and 0 for our formal charges for that structure. All right, how about this structure over here? Well, let's do the formal charges over here. We have 6 valence electrons in oxygen. It's participating in 2 bonds. It has 4 lone electrons, 2, 4. So that means it has a formal charge of 0. My bromine right here, 7 valence electrons because it's in group 7A, 1 bond, 2, 4, 6 lone electrons, so it has a formal charge of 0 as well. This bromine's same as the other bromine, 7 minus 1 minus 6 or 0. And this carbon, 4 valence electrons, 4 bonds, no unbonded, so it has a formal charge of 0 as well. So we've got we have a situation where we have 0, 0, 0 for our formal charges, or a situation where we can have -1 and +1 for our formal charges. Who's going to be better? The formal the structure where the formal charges of the atoms in a molecule are minimized. You can't get more minimized than 0, 0, 0. Therefore, the correct and only acceptable answer on a test is that one, my friends. Chemistry's easy, life is hard, yes? Alright, just in case my last example went over like a milk dud, why don't you write down milk duds? Write down milk duds. M-I-L-K-D-U-D-S. Milk duds. And yes, I have had way too much candy lately. Alright, now that you've written down milk duds, let's take a look at our last example. We've got this fun-filled compound looking at us on an exam. And yes, I promise you, it is full of fun. We've got bromine contributing 7 valence electrons. We have carbon with 4 valence electrons and nitrogen with 5. So our total number of valence electrons is 16. Drawing our skeletal structure is pretty easy. We see carbon, so we know it's going to be the center. So that cuts down on our work. And it costs us 4 valence electrons for 12 left. Nitrogen and bromine each need 6 more electrons to complete their octet. 2, 4, 6, 2, 4, 6. That costs us 12 valence electrons, so we have 0 left over. Is carbon happy at the moment? No. Very sadly, carbon is not happy, because carbon at the moment only has 2 valence electrons, and how many does it want? It wants 4. So we're going to have to share some electrons. In order to do this, we could have an equitable system where bromine shares one end, nitrogen shares a pair, in which case our Lewis structure would be now, the problem with that assumption is, do bromine and nitrogen have equal attraction for their electrons? No. So in reality, we've got a situation where we could also have greed play a role, where we could have, whoops, I erased too much there, where we could have bromine refusing to share any of its electrons and nitrogen sharing 2 pairs. Or, for that matter, we could have a situation where bromine shares 2 pairs and nitrogen's the greedy, selfish pig and doesn't share any. What are we to do? How are we to resolve this dilemma? In reality, which of these Lewis structures will be favored by the molecule? And the molecule will show signs most of which of these Lewis structures. How can we differentiate between them? That's where our formal charges come in. I formally charge you to use your formal charges to solve this dilemma. All right, let's do it. Let's start with this Lewis structure right here. This Lewis structure right here, we've got bromine. Bromine's in group 7A, so it has 7 valence electrons. It's participating in 2 bonds. It has 4 lone electrons, 2, 4. So in this structure, it has a formal charge of +1. Then we've got carbon over here. Carbon has 4 valence electrons, is participating in 4 bonds, so it has a formal charge of 0. Then in nitrogen over here, 5 valence electrons because it's in group 5A. It's participating in 2 bonds. It has 4 lone electrons, so it has a charge of -1 in this Lewis structure. All right, let's move over here to this one. We've got bromine with 7 valence electrons because it's in group 7A. Then we have 1 bond that bromine's participating in, and then we have 2, 4, 6 lone electrons. So that gives bromine a formal charge of 0. Then we've got carbon here, 4 valence electrons. It's participating in 4 bonds. No unbonded, so that gives it a formal charge of 0. Our nitrogen over here has 5 valence electrons. It's participating in 3 bonds. It has 2 lone electrons, so that gives it a formal charge of 0. Whoa! Our second attempt, and what do we discover? We discover right off the bat, we've got a situation where we have formal charges of 0, 0, and 0. So right away, because we know we want to minimize the formal charges of atoms in a molecule, that this is probably our best Lewis structure. And the molecule most probably shows characteristics of this connectivity. However, let's finish the exercise and make sure there's not a resonance situation. So if we come down here and do our formal charges, we've got bromine, 7 valence electrons, participating in 3 bonds, 2 unbonded, and that gives it a formal charge of +2. All right, bromine's +2, so already we know that this formal charge is worse than this formal charge, so there's really no point in even continuing any farther. So the answer on the test would be that one. One more thing. In this class, one of the benefits is you're using a test bank on the computer. And therefore, they do things that you find on nationally standardized exams. As a holdover from the days it was near impossible to put graphics on a typewriter or to put graphics in a computer, a lot of times you'll see exams test Lewis structures by asking you the formal charge on a specific atom. For example, you could see a question that would read, so often you'll see on standardized exams, instead of them asking you to draw the Lewis structure of this compound, what they do is they would say, what is the formal charge on bromine in the correct Lewis structure of this? So what you'd have to do is you'd have to draw all those possible structures, determine which of the structures is best, and what the formal charge is of bromine. And of course we saw from the last slide that was 0 because our best Lewis structure was that one, where the formal charge of bromine was 0. So that's just something to keep in mind. And that's the place you're actually, quite frankly, most likely to be encountering formal charge on this level, is in exercises like that, and an indirect way of asking you about Lewis structures. Well, I hope I've provided you with a great deal of joy during this lecture, nearly as much as an almond joy. Why don't you write down almond joy? Everybody's writing down almond joy. A-L-M-O-A-N-D space J-O-Y. That's it. I'm out of here.